Okay, this is lesson 1.4, sketching graphs and comparing functions. It's standard MA 912.F.1.7. In example 1, it talks about sketching a linear function. They want us to use key features of the function to sketch this graph. So they've already sketched the graph for you, so we're going to identify some key features. The y-intercept, remember the y-intercept is where it hits the y-axis. So this is where 0, -70 is going to be located. That is your y-intercept. Linearity, remember linearity has the word line, so we need to see a graph that has a line, which is we do. The next part, it says positive for values of x such that x is less than -30. Okay, when it says x is -30, it means it needs to be in the positive region. That is where it's located. The next part, it says decreasing. It needs to be decreasing for all values of x. Well, notice that all the values of x, it's showing downhill. They are decreasing. The end behavior is what is the graph doing as x goes to infinity. So in the first part, as x goes to positive infinity, my y values, f of x, is going to negative. So right here, f of x is going to negative infinity. It's decreasing. And then the opposite direction, as x goes to negative infinity, so here our x values are going to negative infinity. Then it says the f of x. Notice that they are positive direction. Our y values are positive. They're going to positive infinity. That's what they're talking about in the graph sketch. So now we're going to try our own. On example 2, it says, sketch a nonlinear function. First thing is use the key features of the function to sketch its graph. The first thing we notice, it wants us to plot the y-intercept. So the y-intercept says it is 0, 3. So on the graph, we're plotting a point at 0, 3. So it's between 0, 2, and 4. There's my y-intercept. It's plotted. The next part says linearity. It is nonlinear, which means nonlinear, we are looking either for a curved graph opening up, curved graph opening down, a V-shaped graph up, a V-shaped graph down, a cubic function, or going up or going down, a reciprocal function, which means it's opening to the right. One of these is what it's asking us to do. So the next thing says it's continuous. Continuous, remember from our previous lessons, means solid line. Next part says positive. All the values of x, it is positive. So by all the values of x is positive, we are looking at something opening up. We are looking at something opening up for the x values. I cannot choose any of the other ones since these are our 3 that we can choose from because they're all opening up positive values. Now the next part says decreasing for all values of x where x is less than 0. Decreasing for all values of x for x less than 0. Okay? Then it says extrema minimum so our minimum value, our lowest point is going to be at the y-intercept. Means our numbers have to be above it. And here's our next phrasing. Our end behaviors. What is the graph doing? So on here, it's saying that as x goes to infinity, so as x goes to the right, my y's are going up. Okay, so it means my graph is going up this way. The next part says as x is going to negative infinity, my y's are also going up. So I'm going up somewhere there. Okay, so again, we plotted the y-intercept at 0, -3. Then it's telling us that the function is decreasing on the interval from negative infinity to 0. What that means is we're seeing downhill as x goes from negative infinity to 0. Then it shows us that we are increasing from 0 to infinity. So we have an increase in our value going there. The next piece it tells us, remember, our intercept is where we hit the y line. So our relative min happens to be the origin where our value is. The number 0, 3, near the origin is where our piece is going to be located. There's our relative min. So again, this is a potential graph of the function. It's a rough sketch. It could have been a parabola that could be narrow or wider. It could have been an absolute value function. Remember, I said there was possibilities of what our graph could be. So I drew a parabola. I could have had an absolute, which was our V-shaped graphs for this situation. Okay, the first thing we notice is that she accelerates 60 miles per hour. Step 2 she does is that she then decelerates to a stop. Then she takes her 15 seconds to reach her maximum speed, followed by 15 additional seconds to come to a stop. It says use the key features. We want to sketch a graph that shows the speed y as a function of x. So then, it says y-intercept. Hey starts her test drive at a speed of 0 miles per hour. So it tells us what our y-intercept is going to be. They tell us the y-intercept is at 0 miles per hour. Now, because she is increasing and then stopping and then decreasing, the function is going to be nonlinear. It is a nonlinear function. The extrema, so those are our extreme values. Her maximum speed is 60 miles per hour, which she reaches in 15 seconds on her test drive. Increasing or decreasing. So it says increasing. Hey, blank the speed at a uniform rate for the first 15 seconds. She increases her speed. She increases her speed at a uniform rate for the first 15 seconds. Decreasing, hey, decreases speed at a uniform rate. Again, for the next 15 seconds until she reaches a stop. Her end behavior, what is happening? Because hey starts at 0 miles per hour and ends at 0 miles per hour, there is no end behavior. In example 3, they want us to sketch a real-world function. So, Hay is test driving a car that she's thinking of buying. She decides to accelerate to 60 miles per hour and then decelerate to a stop to test its acceleration and brakes. It takes her 15 seconds to reach her maximum speed and 15 additional seconds to come to a stop. Use the key features to sketch a graph that shows the speed y as a function of x time x. Okay, so now we need to sketch our graph. So first thing, remember, we need to consider the constraints that we had, our constraints. Hay she cannot drive as a negative speed or a negative amount of time. Distance is a unit of measurement. Never goes negative. So, therefore, the graph can only exist in positive x and y values, which means you can only be located in quadrant 1. That's the only place you can be located in. So, based on what we had, our information, it says, remember, she started at 0, and her maximum speed is 60 miles an hour, and which she reaches in 15 seconds, okay? So, here's our time. Here's our speed. Started out at 0. In 15 seconds, she hits 60. So we need to plot a point at 60. Remember, it is a uniform change, we are going uniformly. So it means we're doing a straight shot up to 60. Then it says she stopped, and then she stopped at 60, and then she decelerated for 15 more seconds back to 0. 15 more seconds, which means for 15 more seconds, if we hit a peak at 15, 15 more seconds hits us at 30. We ended up back at 0, and so we decelerated back to 0. Okay, in example 4, it wants us to compare properties of linear functions. It says use a table and graph to compare the two functions. So the table represents the f of x function, and the graph represents the g of x function. So the first thing it wants us to do is identify the x-intercept of the f of x. So they've highlighted, remember, x-intercepts are always going to be a number followed by 0. A number followed by 0. So then, our x-intercept is located at 3. Then it says compared to the g of x, which is located at -2. So it looks like the f of x intersects the x-axis at a point further to the g of x. We're comparing the f of x to the g of x. If 3, 0 happens to be on the right side of the quadrant on your x-axis, it's the right side. So the f of x equation is going to be to the right of g of x. When we look at the next one, it's talking about the y-intercepts. So again, the y-intercept is where it hits the y-axis. And always it's going to be represented by 0 followed by a number. So it says the y-intercept of f of x, it's 0 followed by a number, is located at -1. The g of x equation, remember, it hits the y-axis, it's at 0, -4. So I'm at 4. So I'm going to plot the f of x equation. It says 0, -1, which means it's down on the negative side of the region. So g of x intersects the y-axis at a higher point than f of x. It's at the top. When we look at the next one, it's talking about slope values. So it says the slope of f of x. So in order to find the slope of f of x, we're going to plot 2 points. So on f of x, slope formula, you need to remember from your previous days, it's the y2 minus the y1 over x2 minus x1. So I'm going to pick 2 points. I'm going to pick these 2 points right here, the 3, 0, and 6, 1. So it's going to go y2, which is 1 minus 0 over 6 minus 3, and I get 1 over 3. So my slope of f of x is 1/3. The slope of g of x, since it's on the graph, you can come positively. We went up 2 units. To the right, we went 1 unit. So I'm 2 over 1. Okay, so each function is increasing, which means both graphs are showing a positive slope, because if I were to plot several points of my f of x equation, 0, -1 is here, 3, 0 is here, which means I am going in a positive direction. But the g of x equation is greater than the slope of the f of x equation. So g of x is going to increase faster than f of x. So when we look at our graphs, the g of x equation has a steeper slope. It's going to have a steeper slope. Okay, in example 5, it says compare properties of nonlinear functions. Remember, nonlinear are our graphs that could be a parabola opening up, a parabola opening down, absolute value opening up, absolute value opening down, a cube function, a reciprocal function, a combination. So it says examine the categories to see how to use the description and graph to identify key features of each function. Then complete the statements to compare the two functions. So it says the f of x says it is the x-intercept is at negative 3.4 comma 0. So I'm using the graph that we have given for the g of x, and I'm just going to use the graph to plot the points. So my x-intercept is at negative 3.4. So 1, 2, 3, negative 3.4. I'm going to plot a point to the left of the blue line. It says my y-intercept, where it crosses the y-axis, is at 1.5. So I'm about at 1.5. So those are my 2 points right there. It says the relative maximum is at this point. So when x is negative 2.3, there's negative 2.3 and 4.7. 2, 3, 4, 5. So somewhere up here is my maximum peak. My minimum peak, or minimum bowl of soup, happens to be at negative 0.4, 1.1. So about here. Let's put it about here. So I went up, came down, hit the y-axis before traveling back up. It's a rough sketch of what the description is saying to us. So we hit the peak, there's a relative min, y-axis, and it's increasing. So it's kind of basically our graph of the g of x, but it's been shifted. It says end behavior as x goes to negative infinity, it's going to negative infinity. Okay, so as our x's went negatively, my y's did go negatively. As our x's went to positive infinity, which they did, our y's went to positive infinity. So we did match our f of x and g of x. So now when we're comparing, it says x-intercepts, we have only one pair of x-intercepts. G of x actually has 3 of them. When we look at our blue graph, the g of x equation, we have 3 of them. We have 1 here, and 1 here. That's why it's negative 1, 0, 1, 0, and 2, 0. The y-axis, the y-intercepts. So the y-intercept on the f of x is at 0, 1.5. On the g of x, it's at 0, 4. Extreme values. Relative max is at 4.7 and a relative min at 1.1. G of x has a relative max at 4.2 and a min at negative 1.2. And end behavior. Let's look at our end behaviors. Our, as x went to infinity, negative infinity, y went to negative infinity. Okay. On the g of x, as x went to negative infinity, g of x also went to they are the same there. As x went to infinity, f of x went to infinity. As x went to infinity, f of x, g of x also went to infinity. This should have stayed blue. Okay, so now let's fill in our chart. So it says the x-intercept of f of x is what to any of the x-intercepts of g of x. So when we look at our f of x, our x-intercepts, we had negative 3.4, which is a negative value, but our g of x equations have an x value at negative 1, which is greater, at 1, which is still greater, which at 2 is still greater. So our x-intercept of f of x is less than any of the x-intercepts of g of x. When we looked at the comparison of the g of x intersects the x-axis, it intersected it 3 times. So it intersected more times than f of x, 3 times to be precise. The y-intercept of f of x, the y-intercept of f of x, our y-intercept is at 1.5, our g of x is at 4. Well, 1.5 is smaller than 4, so the y-intercept of f of x is lower or less than the g of x y-intercept. G of x intersects the y-axis at a higher point than f of x. The relative max of f of x, the relative max, when we look at our relative maxes, f of x is at 4.7, g of x is only at 4.2, so f of x is greater than the relative max of g of x. The relative min of f of x, when we look at our min, f of x relative min is at 1.1, g of x is at negative 1.2, so 1.1 is greater than, so the relative min of f of x is greater than the relative min of g of x. And then we notice that the two functions have the same end behavior.